So today I want to talk about the centripetal acceleration lab, and I want to add one of my pet peeves to the discussion shortly. Okay, so let's start with Newton's second law. There it is. The vector sum of the forces equal mass times acceleration, and the acceleration is in the direction of the net force. We know that from previous experiments and from class. Okay, so today we're going to talk about making things go in a circle. So if something's going in a circle, its acceleration is changing. Acceleration is a vector. It has two parts to it. That is, it has a magnitude and a direction. And I won't go into the details, but I think you can see that if something's, let's just say I'm describing something moving around in a circle here, and it's right here. Okay, so, you know, in the real world, if you're rotating something on the end of a string or rope over your head, and it's over there, you have to pull on it this way to keep it going in a circle, otherwise it's going to go out in a straight line. That is, if you broke the string, this mass would go, I'm looking down at this mass would just go this way in a straight line, because there's no acceleration. There's nothing to accelerate it. So things that don't have an acceleration have a net force of 0, which means they're in equilibrium. This would be moving equilibrium, and they move in a straight line at a constant speed unless a force acts upon them. So this is what Newton had to sort out, and it took all the time from time 0 to 1690 roughly for Newton to figure this out, and he was a genius, and it took him 14 years to do this. And explain that forces are the things we need to focus our attention on if we want to talk about why things move in the directions that they move. Okay, so anyway, if this rope broke right here, this object, again looking down on it, would just go off in a straight line. And of course gravity, if it's not on Earth, gravity would slowly make it fall to the Earth because it's a projectile, and we know all about those from the earlier chapter. So anyway, we're not going to break the string. We're going to keep this thing moving in a circle. And so the string holds it into going in a circle. And so there's tension in the string. Tension is, of course, it's a special word we use for certain forces in certain circumstances. And there's a tension in the string everywhere you are. If you're up here, you have to pull this way to get to go in a circle, and otherwise it would go off in a straight line if the string broke, and so forth. So there's always this constant tension, and it's constant. Maybe if we rotate this around at a constant speed, if the velocity is the same, the magnitude of the velocity is the same everywhere, then the tension is constant. Okay, let's take a look at this. So this is Newton's second law in general. Let's apply it over here. I'm going to add a little c here and a little c here, just to remind us that it's going in a circle. C stands for circle, it stands for centripetal also. It's really handy. So, there's some kind of a force making it go in the circle, accelerating it, because it's not moving in a straight line. It's not moving at a constant speed in a straight line. If we keep it moving at a constant speed, which we're going to do, but it's not moving in a straight line, then the vector acceleration is not 0, because you've changed the direction of this vector, which means you've changed the vector. If you can change its magnitude, you can change its direction, you can change both. We're going to keep the velocity constant, so the magnitude is not going to change. And you will find out, if we haven't already talked about it in class, that the centripetal acceleration is given by this expression, v squared over r, the radius of the circle that it's moving in. So this assumes circular motion, and right now we're going to assume circular motion at a constant speed, and therefore the acceleration is a constant magnitude vector, but it's an acceleration, of course, pointing this way. So this force, this tension force, causes an acceleration in the direction of the net force. This is the net force. I'm ignoring gravity in this case. Actually, it's comparatively small, but in the horizontal plane, gravity is perpendicular, vertical, and so it doesn't enter into the force discussion here. Only this tension force, the force in the string, is the force we need to keep this thing going in a horizontal circle, for instance. And acceleration is given by this centripetal acceleration, that is the magnitude of the vector. Centripetal acceleration is given by that. Again, if V is constant and R is constant for a circle that it is, we have a constant magnitude acceleration, but it's an acceleration that's always changing because its direction is always changing. And that's the big point here. So we're going to have constant magnitude accelerations, which means this tension force is going to be also constant in magnitude, but of course it always changes direction as you're trying to keep this thing rotating in a circle. So my point is, my little soapbox that I want to get into right now, is that there's no new special kind of force here. It's simply tension in the rope or tension in the string. And we've talked about tensions in strings, and we will talk more about them in the future and do experiments involving tension. That's the situation here. So there's this force which has constant magnitude thanks to the constant acceleration and the constant mass. That's the mass. And it's moving in a circle, changing its direction, which means it's a vector that changes direction but not magnitude. So we're mainly going to worry about the magnitude now that we know the geometry of the situation here. There's not a new, I'm not going to say it, special kind of force that causes things to move in circles. Gravity can cause things to move in circles. Ropes can cause things to move in circles in this case here. And so I'm not going to label this as a special new kind of force. It's simply an old force we're very familiar with, tension. That's it. Okay, so don't get any new forces here. We use our very small box or bag of good old forces like tension and the force of gravity and friction and things like that. We just don't have too many different kinds of forces that we've defined that we need to worry about in this class so far. We don't have too many more, really. Okay, so this is the theory behind this. So if you multiply an acceleration by a mass, you get a force. That force is the force supplied by tension that causes it to move in a circle, and that's one of the forces, which is pretty tricky to get. We'll have to talk about how to do that in the apparatus that we have. Get the magnitude of that force. Okay, so let me also talk about another way you can stretch a spring, because really what this lab is all about is the spring constant. And I think you know from everyday experience that when you have a spring, the farther you stretch it out, the harder you got to pull, and it's this very simple linear relationship. And it looks like this. Sometimes there's a minus sign in there depending upon if there's you and there's a spring, we have a pair of forces, and we have to, by Newton's third law, figure out which pair we're talking about, which of the pair of forces we're talking about. If we're talking about the force that the spring supplies, there's a minus sign there because the spring wants, if you pull it this way, it wants to go back that way. It's kind of ornery like that, so that it needs a minus sign. But if you're talking about the force you're supplying to pull it this way, then you don't need the minus sign, because that's the force that's in the direction that you're pulling it. That's your force. So we have two bodies, we have a spring and you, and they have a pair of forces. One's in one direction and one's in the opposite direction. Let's just not worry about the minus sign here. So let's talk about the force that needs to be supplied here to make this go in a circle, and also to let me get one of these apparatuses. Here is the mass that we're going to use. Not this whole thing, just this little mass on the end of this spring. Okay, and so this little mass, and by the way, the size of the value of the mass is stamped on the end of this cylinder, which is the mass that rotates around. It's about 150 grams, thereabouts. So the spring, as the mass rotates around, the spring is going to get stretched because you have to have a certain amount of tension to supply the right amount of force to make it go in a circle with the right radius. The mass we're studying is this mass, which is about 150 grams, and it's at the end of the spring. So if we rotate this, which we'll see how to do that in a bit, the rotation depends on the force on this spring, the tension produced by the spring on this mass depends on what we just talked about, the mass times the velocity squared over the radius that it moves in. So we need to measure the radius, of course, that's another tricky thing in this we'll have to do. So anyhow, there's two ways to stretch a spring out. The easy way is to just pull on it and stretch it out. Okay. That requires a certain amount of force. And of course, the tension in the string that I have down here is the same tension as if you stretch it out the same amount as the tension needed to make it move in a circle. So we've got two ways to measure the force needed to stretch the spring out to a very special position, which I'll talk to you in a minute about. So either way, we can find the spring constant. So we find the spring constant by measuring the force needed to stretch at a certain distance. And of course, F over delta x is k. That is, if we stretch at a certain distance, we see that this divided by the distance that we stretch it, so there's a delta, it's a displacement really, gives you the spring constant. So if you simply put this on a hook and add weights, and more weights and weights here, until it stretches a certain amount, which we have to talk about very carefully, then as you change the spring length, which you change by turning this knob here, the more you turn it up towards 20 on the dial, this is the dial from 0 to 20 here, the longer the spring is, and the more force you're going to need to stretch it to the same position, same reference position. So this simple experiment is hang this up on a stand, put a weight pan down here, we'll show you that in a minute, and pull it out until it's stretched to a certain reference position, which we're going to look at. So you're going to do that for 5 different stretching distances. Unfortunately, these threads on this screw here are 40 threads per inch. I apologize for the units, but 40 threads per inch. So every time you turn this knob around once, the distance, the stretching of the spring changes by a 40th of an inch. Of course, you have to convert a 40th of an inch into preferably meters. That's not very many meters, so it'd be 0.00 something meters. So we're going to do this for spring stretches of 5, 0, 5, 10, 15, and 20. So this could be the 0. I'm not going to mark this 0, 5, 10, 15, 20 because you didn't mark this in meters, and this needs to be in newtons, standard SI units. So when you do that, you'll find that, of course, the more the spring is stretched, the more force you're going to need to get it in position. And these are these 5 data points. So this is the easy part of the experiment. You know how to do this. You put it in graphical analysis. You draw a straight line, the best fit straight line through those points, and the slope is the spring constant. Pretty much. Okay, well, that's the easy part, and the harder part is to do this literally on the fly as it's rotating, because the faster it rotates, the bigger the velocity is, and the bigger the velocity is, the more force you're going to need to keep it going in a circle at a certain special radius, which we're going to talk about. So that's the easy way to get K. And of course, the bottom line here is compare your experimental value for K by just stretching the spring out with some weights to the experimental value of K that you get by rotating it and supplying the tension F sub C or T, whatever you want to call it, that you need to make it rotate in that same circle of the same radius. Okay. So let's talk about that more complicated second part. And we'll show you that in the apparatus. And also there's some tricks to doing the experiment that we'll talk about. Okay, so the radius of the motion of this object is defined. We talked about this when we did the first experiment, the center of mass idea. So the center of mass in this, since we're looking horizontally, the center of mass in this direction is the distance from the center of the axis of rotation to the middle of this mass. And there's a scribe mark right in the middle of the mass, indicating the center of mass of this little cylinder in this direction. Okay, so that's what we need to measure very carefully. We'll show you that. Of course, we're not going to measure it on the run. We're going to measure it when I'm hanging down nice and quietly at the right spot. We'll talk about that later. So, I'm not sure what to say here. And so in the second part, we're going to calculate the tension needed, F sub C or T, or whatever you want to call it. It's the tension in the spring that we have F sub C equals mv squared over R. Okay, or you can call it T, whatever you want to call it, but it's not any special new force. It's some old force that we know and we've already talked about. So the mass is the 150 grams roughly mass at the end of the spring. And you need to have an instrument that measures this is called tangential velocity. If something's rotating around in a circle like this, and it's here and it's going that way, this is its tangential velocity, because it's tangent. It's moving this way tangent to the curve. Tangent to the curve at that point. And it's over here, it's moving tangent to the curve at that point. So it's a tangential velocity. Okay, so our goal is to measure the tangential velocity, which is tricky, and also the radius of the circle that it's rotating in, but not while it's rotating, but when it's just hanging there quietly, so we can measure it. We're going to do that for settings of 0, 5, 10, 15, and 20 and 40. It's an inch converted to meters on this scale. And we'll show you in a little more detail how to set this dial. So here's the easier part, to find the force needed to stretch the spring to a certain distance. And you've got a picture of the balance condition, as I call it, and that's where this pointer here is pointing at this, I don't know what else to call this, but a little mushroom tip. So I've got the right amount of weight down here. You have to add all these weights. If you need to check the weight of the pan itself, you can use your balance to do that. Again, all these weights are, especially the old beat-up ones, are only guaranteed to 1%. So your error in this weighing overall is 1%, whatever the weight is, whatever the mass is. So this is balanced. I'm only using masses down to 10 grams. Don't get carried away with 1 grams and 2 grams and 5 grams, because we've got about 3 kilograms down here, and 1 gram out of 3 kilograms is 1 out of 3,000, which is, you know, a pretty small percentage error. So just get it, balance it to the nearest 10 grams, and be happy with that. Okay, so it's balanced, and again, this is for the 0 setting, and I've got it set up so that this just barely doesn't hit the table, so in case something breaks, you don't have a big tragedy. So that's how to do it for the gravitational, F sub G if you want to call it, the gravitational force, the weight needed to pull it out. Don't forget, you got to multiply by 9.8, change that into kilograms. And we do that for 0, 5, 10, 15, and 20 on the dial. Convert those to meters before you graph things. And you should get a spring constant in newtons per meter, which is, I think, going to be around 500 or 600 newtons per meter. Pretty big number, because that's a pretty stiff spring. Okay. Let's see what else. While it's in this position, and notice, well, a couple of nice things about this. You notice when it's in the balanced position that this spring, the center of mass of this spring itself, is right in the middle along the shaft, the axis of rotation. They've designed this so that the mass, spring mass, has no effect on the experiment, because half of its mass is up here and half of it's down there, and those two cancel each other out as it's rotating. That's really very nice. So this is a very clever gizmo. But it could have been more clever if they'd used millimeters. But can't have everything. So that's balanced. That's a balanced condition. So now you need to measure the radius, which is a little tricky, and you need to do that a few times, as we know, to get a good average. And you need to measure, with some difficulty, the distance from this line here, the scribe line, to there's some little bosses here which have lines in them, which indicate the center of the shaft here, which is the center of the circle through which this thing rotates. So you need to measure this very carefully, and it's with some difficulty to measure from this line to something like that. I will not do it carefully. You do it more carefully, and of course read the radius here, and do that a couple times. Also, if you're really observant, you'll notice that this little weight there, the mass we're using for the rotation and the other experiment, is a little bit crooked. It's pulling down a little bit crooked, which means you've got to measure the radius on this side and the radius on the other side, because it might be a little bit different, and take an average. And so I would measure it 2 or 3 times on this side and 2 or 3 times on that side and take an average. That's a critical number. In fact, if you do a maximum deviation analysis with your radius values, you'll find that that's probably one of the bigger error sources in the experiment. Okay, so you have to keep in mind these error sources. 1% for any amount of mass you have down there, 1% is always the same. And the radius, you get the maximum deviation in your radius by averaging the 6 numbers and looking for the worst one that's farthest from the average, turning that into a percent. So I'm going to percentify, so to speak, all of your error sources and add them up at the end. This lab has a little bit of a trick to that, because the velocity, when we calculate the velocity in the more tricky way, it appears in the formula v squared over r. The radius appears in the formula. To get v, to get the velocity, you have to figure out how many meters does it go when it goes around once. That's the circumference. And you have to multiply that by how many times it's gone around in a second, or a minute, in a second, ultimately. And that will give you the velocity. It's going to be somewhere around 3 meters per second. typically. So if you want to get a number that's pretty close to 3 or 4 or 5 or 2 or whatever, then you've done a unit conversion error, which is easy to do in this lab. So anyway, rotates around about 3 meters per second. That's about 5 miles an hour, and that's what you need. Then let me show you also. Let me take this apart. Now, when you, and it's really hard to see this, but I've got this set so the Scribe Mark, there's a mark on, and there's a picture of it in your handout also, but there's a mark on this, on the face of this big knurled knob that's got a Scribe Mark, which is what you want to set pointing towards the scale. Now, you may have noticed that it wasn't exactly at 0 when you looked at it in the picture that we showed you a bit ago, but it's close enough to 0, we'll call it 0. So it's 0. Now, when you go to 5 and 10 and 15 and 20, you watch that Scribe Mark. Don't look at the scale, it's way too fine. Watch that Scribe Mark and rotate it around 5 times. That's 1, that's 2, that's 3, that's 4, that's 5, and point that Scribe Mark back where it was before at that scale. And that's pretty accurate, because you can guess that where that Scribe Mark is within a few degrees out of 360. So that's pretty accurate. And you have to, the error there is also reduced by a factor of 5 because you've done it 5 times, not just once. So the error in setting this is very, very small. I think you can safely forget about that. But now if you look at the scale, we'll call it 5. Whatever it is, you'll call it 5, because you know you've turned that around exactly 5 turns, and it's 5/40ths of an inch longer, and it's going to take that much more force to stretch the spring out to the same place. You don't have to measure the radius more than at one time when it's balanced, because it's always the same. This thing, when it rotates, the radius from the axis of rotation to the center of mass of this is always the same number. The spring is different positions here, but you're not measuring that. You're measuring how far away from the center of mass of this is it from the axis of rotation, which is always the same. So that's nice. We're now going to do the second part, which is running it, measuring it on the fly, literally. So we're going to rotate this thing, this apparatus, at the correct speed to produce the correct velocity, tangential velocity, to make it, to have the tension supply the right force to balance this again. So you rotate it faster, it's going to balance farther out. You rotate it slower, it's going to balance farther in. It's the same trick is to balance this while it's rotating. That's pretty exciting. Okay, let's do that. So this is the rotation apparatus, and first of all, it has a chuck here, which is like a drill chuck. And you want to put this in all the way and rotate this chuck until it clicks a couple times. That means it's really grabbed onto that shaft. We don't want these things flying across the room, please. Okay, so there's some finesse in operating this, and after a couple of years, I think I've got some of the secrets of how to operate it. So I'll try to pass those on to you. Also, when you turn this on, it has a little whistle that tells you it's on, so that you don't forget that this thing's rotating. It can smash into your head. So be careful. We'll turn this thing on, and it's got an up button and a down button. Now it's kind of like setting your alarm clock, or setting something that's got an up and down adjustment, like volume control and so forth. If you just push it for a little bit, it's only going to go up a little bit, and if you push it for quite a while, it's going to ramp up a lot more. So you got to be a little careful to push it a little bit less and less in terms of duration as you get closer and closer to your balance point. So we're going to do this, and you will be able to see, and it might be good to have something like this in the background, but don't smash your hand, so that you can, all this other stuff is distracting you, so you can watch that little pointer, because it's going to be pulled out and it's going to balance again at the balance point, just like it is now, but while it's rotating. So you're going to be able to see that, especially if your partner kind of is careful and holds something back that's neutral or uniform. So let's turn this on. So it's set for revolutions per minute. There's also a freeze button in the middle here, which freezes the display, which is what you want to do, because this is kind of a dynamic thing. You're not going to get it to balance just right and just sit there. It's kind of vibrating and jumping up and down and things like that. So it's not going to be steady. So when it passes through the balance point, you hit the freeze button and freeze that reading in. So we're going to measure it 2 times as it's going up to higher speeds and 2 times as it's going down to lower speeds, and take those averages again. Again, you got the maximum deviation, you got a percent error, and that's another big error source in this. If you have plus or minus 2 RPM out of 500, that's a pretty good experiment. So now I'm letting up on this. There's a lot of inertia here. It takes a while for this thing to speed up and level off. So it leveled off. The last number I saw was about 220, and it's leveled off at 217. So it will level off. If you just leave it alone for a while, it will level off at the last number you saw on that screen. So let me crank it up to about 500. It's going to go up pretty fast because I'm holding it down for a long time. Oh. So the last number I saw was 480. So it's gone way past that because I held it down for too long. So you'll also notice, and you probably want to take a look at this more carefully. We'll move the camera in for a better look in just a minute. So it's reading about 570, and I'm going to increase it slightly and then try to freeze it. This freeze button seems to be a little finicky, so I'm going to try to read at the same time where the pointer goes past the mushroom. Oh, now it's exceeded it. So now it's above the mushroom, and it's reading about 598. Let me lower it just a little bit. It seems to be changing by itself, so it's now at 570. So why don't I just leave it go, and then when I see it go past the mushroom, it seems to be speeding up and slowing down on its own. Okay, there it is, 588. And now it's slowing down. How nice. Okay, it's below the mark. Whoa, there it is, 592. It's gone above the mark, and now it's going to slow back down. It already did that. I wasn't watching. So I guess if you just kind of leave it around 590 and watch it, and since you have a lab partner with 2 extra eyes, you can just say, read it, and they can read the dial here instead of trying to push the freeze at the same time. So it's below the mark. Now it's above the mark. It's read 592 or thereabouts again. And just let it slow down by itself. There it is again. So between you and your partner, you can just indicate to mark it, and then watch it go up and down a couple times and get an average. So I've been playing with this particular apparatus, and I see that the freeze button isn't working all that well. And so rather than complicate the issue, since you have a lab partner, and nobody should try to do this by themselves, if you have a lab partner, then as the pointer rotates above on the way up or on the way down, pointing to the mushroom, you just say now, and your partner will read whatever's on the display. That's a whole lot easier than trying to coordinate. You're watching this with the button pushing and being in the wrong place where you're trying to push the button and the button's not there. So, or it doesn't work. In this case, it didn't work well. So I would just use your partner, do this as partners, and watch this go up and down and get around the right RPM, and just call now when it goes past on the way up and when it goes past on the way down a couple times, and take an average. So it's a little tricky, but it's kind of an exciting experiment. So.